Hello. So, welcome everyone to lesson 2B, solving absolute value inequalities. So, if you are here just to look at a problem that you are having questions with, make sure to subscribe to that problem. Otherwise, let's get started. So, there are two cases when we are solving absolute value inequalities. The first case is when we have a greater than or equal to. So, remember that absolute value represents the distance from 0 and x that is greater, in this case, for this example, greater than 5. So we are looking for all of the values when taking the absolute value of x that are greater than 5. So when we take absolute values, we know that there's usually going to be two solutions. The first solution is going to be on the positive side, so we're going to start where the absolute value of x is equal to 5. And on the positive side, that's going to be 5. So we're going to put a dot at 5. The reason why we put a solid dot is because we know that it is greater than or equal to. And if it was a less or greater than, just a regular greater than, then we put a open dot. So since it's greater than or equal to, we know that we are going to put a solid dot. Since we know that x, when x is equal to 5, positive 5, we know that this is equal to. So we're going to put a solid dot. Next, we are going to look at the negative side. Well, what negative number, when taking the absolute value of, equals to 5? Well, that is going to be negative 5. Because when we take the absolute value of negative 5, it's going to be 5. And we get 5 is equal to 5. So we know this works. So we are also, and since we know it's greater than or equal to, we know that it's going to be a solid dot. So now we have our 2 points, negative 5 and 5. Here is where we are going to add in the inequality side of everything. So since we have the absolute value of x is greater than 5, we know that we have to plug in numbers into x that after taking the absolute value, we get greater than 5. So we know that if we plug in the absolute value of, let's look at the positive side first, and we took the absolute value of 4 and we plugged it in to our original equation. If we plugged this in right here, where x is equal to 4, we know that this does not satisfy our equation. So we know that 4 is not an answer, albeit 2 or 3, 2, 1, and 0 are not our answers either. We do know, however, that 6, if we plug 6 in for x, absolute value of 6 is greater than 5. So we know that this works, and we know that this is a point. And 7 is a point, and 8 is a point. 8.5 is a point, 9 is a point, and we know that it goes on forever and ever as it approaches infinity. So every number from 5 and above is going to be a point that satisfies this equation. Now, let's look at the negative side. If we plugged in negative 4 is greater than or equal to 5, well, the absolute value of negative 4 is going to be 4, and 4 is not greater than or equal to 5, so negative 4 doesn't work. It goes for negative 3, negative 2, negative 1, and 0, so those don't work. Same thing as last time. If we plugged in negative 6 for our absolute value, the absolute value of negative 6 is going to be 6, and we get 6 is greater than or equal to 5, and we know this is a point. Same as negative 7, negative 8, 8.5, negative 9, 10, and we know that this graph goes on towards negative infinity. So, as you see, our greater than when we are graphing our greater than, we know that our graph is going to diverge from each other. It's going to go in the opposite direction from each other. The positive is going to the right, and the negative is going towards the left. So, for the interval notation, we want to read from left to right, and we want to go from the leftmost point. Well, the leftmost point, as y'all see, is continuous. So we know that we are going to approach negative infinity. So we are going to put on our first negative infinity, comma, and where do we stop? As we read left to right, we stop at 5. And since we include 5, we're going to use a bracket. This U just means that we're going to unite these two rays or these two lines together, and we pick back up. As you see that we don't go towards any of this, so we cannot include it into our interval notation. We pick back up at 5, and since it's included, we're going to use this should be -5. Since we pick up back up, since we include 5, we're going to use a bracket, and we see that we are going to go on forever towards the positive direction. So that means we are going towards infinity. Our next case is, of course, less than or equal to. So, just like the greater than or equal to, our example represents the distance from x and 0 that is less than, in our specific example, less than 8. So we want to find all the values of x when taking the absolute value of it to be less than positive 8. Well, we are going to do the same thing. We're going to set x, absolute value of x, equal to 8 to find out. Well, absolute value of x is equal to 8. We get two solutions. We get x is equal to -8 and x is equal to 8. So we're going to put those as our 2 points. And since it's greater than or equal to, we know that's going to be solid points. Now, we want to find all the x values when taking the absolute value is less than 8. So if we looked at the positive side and looked at the number 9, if we took the absolute value of 9 and set it towards our equation and say x is equal to 9, we get absolute value of 9 is less than or equal to 8, or 9 is less than or equal to 8, and we know that this does not work. So 9 does not work, albeit 10, 11, or 12, or infinity would not work. We do know that if we took the absolute value of 7 and put it into our equation, we get the absolute value of 7 is less than or equal to 8, or 7 is less than or equal to 8. We know that this works, so we know that 7 is going to be a point on our equation. 6 is going to be a point in our inequality, not equation, inequality. 5, 4.5, 4, 3.5, all the way down towards -8. Now, let's see if this line from the positive goes all the way towards the negative side. Well, if we did -9, if we took the absolute value of -9 and set it less than or equal to 8, well, the absolute value of -9 is going to be 9. And is 9 less than or equal to 8? No. So we know that -9 doesn't work. Same with -10, -11, -12. So we know that all the numbers past -8, smaller than -8, are not going to work. Well, let's look at the numbers that are higher than -8 or more or larger than -8. If we took the absolute value of -7 and set it equal to or less than or equal to 8, the absolute value of -7 is going to be 7, and we know that 7 is less than or equal to 8, so we know that this works. So we have 7 as a point. -6 or -7 as a point. -6 -5, -4, -3, -2, -1, -0.5. And we see that on the negative side, as we move across, we're going to go towards +8. So on a less than graph, you are not going to go towards infinity. You're actually going to go towards each of the points. They are going to converge or combine together to make one solid line. And you see that it doesn't continue past those 2 points that you found. So a rule of thumb, when you have a greater than or greater than equal to, you are going to diverge. You're going to diverge from each other. When you have a less than or less than equal to, you're going to converge. You're going to go towards each other. So to write the interval notation of this, we want to state that all the points between -8 and 8, -8 and 8 are going to be included in our inequality. So we're going to state that the bracket of -8, because -8 is included in our answer, comma 8. And we're going to use a bracket again because we know that it's going to be included in our answer. All right, so now we're going to get to the meat and bones of this lesson. We are going to solve for absolute values, inequalities, and then graph them out. So just like when we are solving absolute value equations, we are going to isolate our absolute value term. So since we want to isolate x plus 5, the absolute value of x plus 5, we need to get rid of this -3. To get rid of this -3, we're going to add 3 to both sides, and we're left with x plus 3 is greater than 4. From here, I now know that my absolute value expression is isolated, so I get x plus 3 is greater than 4. I want you all to now write down and note that this is a greater than problem. We can determine now that this graph is already going to diverge. We can only tell this after we isolate our absolute value expression. We cannot say that this is going to diverge because we have a -3 on the same side as x plus 3, or the absolute value of x plus 3. So make sure that when you are determining what type of problem this is, you have to isolate the absolute value expression first. So now we're going to create two inequalities. The first one is for analyzing the positive side of our number line. Remember, again, absolute value, we analyze the positive side and the negative side. So the first inequality is going to be the positive side. And we are going to keep each side and the inequality symbol the same. So we're going to keep the x plus 3 the same. We're going to drop our absolute value bars since we're analyzing practically the absolute value. And we're going to keep the inequality the same and the number on the other side the same. So practically, it's a carbon copy. Now, our second inequality is going to be the negative side. We're going to analyze for the negative side of our number line. So to do this, we're going to keep our inequality the same. So we're going to do x plus 3, but we are going to flip our inequality and switch the sign of our other side. So you see here, I flipped the inequality from greater than to less than, and I've switched the sign from a +4 to a -4. So that's how we are going to create our two inequalities. It's fairly simple. All we have to do now is solve for our inequalities. So we're going to do our left-hand side first. X plus 3 is greater than 4. We're going to subtract 3 on both sides. And we get x is greater than 1. Then we're going to do our right-hand equation where the x plus 3 is less than negative 4. We subtract 3 on both sides, and we get x is less than negative 7. So now we have our two x values. Our two x values. Remember, whenever we have a greater than problem, we know that our graph is already going to diverge. It doesn't matter what the points are or anything, we already know that this will be diverging. So when we are going to graph it out, we draw our number. We're going to draw out our number line. We're going to start 0, and now we have our 2 points right here. We have point number 1 and point number 2. So we're going to put our point as 1 here, and then our point as negative 7 here. Since this is a greater than problem and not a greater than or equal to problem, and you see that these inequalities do not have an equal sign or a line underneath the inequality, we know that we're going to use open dots. So we're going to use an open dot for negative 7 and an open dot for 1, because these points are actually not included in our answer. If we plugged 1 in for x, we know that 1 is not greater than 1. It has to be equal to 1. So we know that it's going to be diverging from each other, but we can also tell because of our neat little trick. If we have a greater than, we can draw our arrow. X is going to go towards or going this way from 1. So we're going to push and go to the right. X is going to, on the right hand side, on the negative side, x is going to push towards the left side. So we're going to go towards the left side. And we see that our graph diverges from each other. So now let's do these problems. Our absolute value inequality is already isolated, so we're going to split it up into two inequalities. This should be fairly easy, as it's just like these examples right here. These examples right here, case 1 and 2, but we're going to go through it anyways using our new steps. Since it's already isolated, for our positive side, we're going to keep everything the same. For our negative side, we're going to keep our absolute value the same. We're going to flip our sign, and we're going to flip our number, or switch our numbers value. So now we know that our 2 points are going to be 7 and negative 7. And since we see that this is a less than problem, we know that this is going to converge or go in. So we know that this is going to go towards, so negative 7, all the points towards 7, and 7 towards all the points of negative 7. So our interval notation here, since it's less than and not less than or equal to, we're going to use parentheses because negative 7 and 7 are actually not included in our answer. So now let's look at the second problem. We want to isolate our absolute value expression, so we're going to divide both sides by 3, and we're left with 2x plus 5 is greater than or equal to 3. Now we're going to split this up into two equations. We get 2x plus 5 is greater than or equal to 3, because we're going to keep everything the same for the positive side, and 2x plus 5 is less than or equal to negative 3, because we're switching the sign and the number of the negative side. All it is now is to solve it. We're going to do our left-hand side first, our positive side. We're going to do greater than or equal to negative 2 and 2x. Divide both sides by 2, and we get x is greater than or equal to negative 1. So now we're going to do our right hand side. We're going to subtract 5 onto both sides, and we're left with -8 2x. Divide both sides by 2, and we get x is less than or equal to -4. So we cannot say that this is a greater than problem until we isolate our absolute value expression. So we actually use this equation right here to show that we are a greater than problem. That means this is going to diverge or go out. So we have our 2 points, -1 and -4. So we're going to look at those 2 points. We're going to plot our -4 and plot our -1. I'm using solid dots because it is greater than or equal to, greater than or equal to. So I'm going to use solid dots because -1 and -4 are actual solutions on our graph. So since they diverge, I'm going to pull them out, outside and away from each other. Let's look at number 3. So number 3, again, we want to isolate our absolute value expression. So we want to get rid of this 16, -16, and this -3. Remember that you cannot combine these two because these are two separate terms. We could say that y is equal to absolute value 2x minus 5. And we can say that this is -16 minus 3y is less than -49. And you all know that we cannot simplify this. So treat the absolute value expression the same way that you would treat, let's say, a variable. So we know that we cannot combine -16 and -3 by subtracting. We want to get rid of this 16. That means we want to get this 16 to equal to 0. So we're going to add 16 to both sides. And we get -3 is the absolute value, or times the absolute value 2x minus 5 is less than -33. Well, I'm not done yet. I still need to get rid of this -3. And since this -3 is being multiplied, I'm going to divide by -3. Now we are going to do a flash to the past. And we're going to look back at Algebra 1 material. And whenever we divide or multiply by a negative number in an inequality problem, we know that our sign is going to flip. So it's actually going to switch. So from a less than, you're actually going to go now to a greater than, since we divided by a -3. So we divided by a -3. So our new equation is going to be 2x minus 5 is greater than positive 11. So this is the key takeaway. I cannot use this expression right off the bat to determine whether or not it's less than or greater than, or less than or greater than problem. So we can't use that. Can't use this equation. We have to use our isolated value equation because it can switch based off dividing a negative number. So this is now a greater than problem, even though it used to be a less than problem. So we are now going to use a greater than, or so now we're going to solve a greater than problem. So now we know this is going to go outwards. So split our inequality into two sides. And for our positive side, we're going to keep everything the same. 2x minus 5 is greater than 11. And for our negative side, we're going to flip our sign and flip our number again. So this again means that we're going to flip our sign back to less than. I know it can be a little confusing, but I'm sure that you all will get the hang of it. So we're going to do less than negative 11. All it is now is to solve for x for both equations. We're going to start with our positive side, of course. And we get 2x is greater than 16. Divide both sides by 2. And we get x is greater than 8. Now on to our negative side, we did plus 5. And we get 2x is less than negative 6. Divide both sides by 2. And we get x is less than negative 3. So now we have our 2 points, and since it's not a greater than or equal to, we know that our circles or our dots are going to be open. So we get an open dot at 8 and a open dot at negative 3. Since we know it's a greater than or equal to, we are going to diverge or go outwards. So let's look at the next problem. So we want to isolate again our absolute value expression. So we're going to remember that we cannot combine these two. We have to treat this as one whole term. And since these are not like terms, we cannot combine them. So we're going to get rid of this 10 instead. I'll use a different color this time. Subtract both sides by 10. And we get negative 3 over 2 times the absolute value of 3x minus 9 is greater than or equal to negative 9. Now we are going to multiply, since we want to get rid of a fraction. To get rid of a fraction, we're going to multiply by its reciprocal. So we're going to multiply by negative 2 over 3 and multiply this side by negative 2 over 3. Well, we're multiplying and dividing by a negative number. So what happens to our inequality? That's right, it flips. So instead of a greater than or equal to, we get a less than or equal to. And now we're going to get our new equation, 3x minus 9 minus, or well, not minus, but make this into a fraction. Negative 9 times negative 2 is positive 18. And 1 times 3 is just 3. So our equation simplifies to the absolute value of 3x minus 9 is less than or equal to 6. So we now have a less than or equal to problem, even though we started with a greater than or equal to. So again, since we know now that our isolated equation is a less than or equal to, this is going to be a less than problem, or a less than case, and we are going to converge, or go in. Create our 2 equations. We get 3x minus 9 is less than or equal to 6. And 3x minus 9 for our negative side, flip the sign, and flip the number. We're going to add 9 to both sides for our left side equation, or inequality. And we get 6 plus 9 is going to be 15. Notice how I did not switch the sign from here to here. Remember that we only switch the sign when we are multiplying or dividing by a negative number. Since we're multiplying by negative 2/3, we're going to flip the sign. But since we are adding or subtracting negative 9 or positive 9, we do not flip. So flipping the sign only matters for multiplication and division. Last but not least, we're going to divide by 3, and we get x is less than or equal to 5. Now we're going to do the same thing on the right side. We're going to add 9. And we get less than, oops, pen's bugging out, or greater than or equal to 3x plus 3. Divide both sides by 3. We get x is greater than or equal to 1. So we have our 2 points, and we know that it's going to be less than or equal to, so our 2 points are going to be included. That means we're going to have solid points. So we have 1, not at -5. We have 1 at 1, and we have a point at 5. Since it's a less than problem, we know that they're going to both converge, so we're going to say they're both going to converge towards each other. Now we're going to talk about 2 special cases with absolute value inequalities. But first, we're going to fix this problem. I didn't fix it when I was creating the notes. This should not be a less than. This should be a greater than. Trust me, it's just going to be a greater than. There's no gimmick to it or anything like that. I just messed up writing the problem. So now we are going to deal with just solving out this problem. Can't combine this -3 and this -6. Remember, they're not like terms, so we're going to add 6 instead to get rid of this 6. We get -3 or -3 times x plus 2 is greater than 6, 3. Now we're going to divide both sides by -3. And since we're dividing by a negative number, our inequality flips and we get less than. So we end up with x plus 2 is less than -1. Now I want you all to stop here. We have to remember that an absolute value always has to be a positive number. So can a positive number ever be less than a -1? This is false. We know that a positive number, no matter what we plug in for x, if we plugged in -1 million, -1 trillion, we know that the absolute value would take whatever is in that problem and make it positive. So a positive number cannot be less than a -1, or a positive number cannot be less than a negative number. So this is going to be false. And since we have a positive less than a -1, we say that this is a no solution. So we say that this is no solution. So just for formality's sakes, when the absolute value is less than or equal to a negative number, then no solution. So when we see the absolute value of an expression is less than a negative number, or a absolute value of expression that is less than or equal to a negative number, these two expressions will yield a no solution. So now that we've seen no solution, we're now of course going to see all real numbers or infinite amount solutions. So we're just going to solve the same exact way as we usually solve. We're going to add 3 to both sides to get rid of it, and we get greater than or equal to -12. We have 4 times x plus 2. We divide both sides by 4. And we get x plus 2 is greater than or equal to -3. Now remember that we didn't change the sign because we're not dividing by a -4. So this stays as a greater than. But now I want you all to stop again. Remember that the absolute value always has to be positive. So no matter what x value you put, even if you put -infinity, -infinity plus 2 is going to be -infinity, but the absolute value of -infinity will be positive infinity. So we have a positive number that is greater than or equal to -3. Well, no matter what x value you put in, you know that this is always going to be true. Even if you put the lowest negative number, you know that it's going to be true because the absolute value always creates a positive number. So this is always true. So since it's always true, we have infinite amount of solutions. Because no matter what x you put in, or no matter what real number you put in, you're always going to satisfy this inequality. So, just for formalities, when the absolute value is greater than, or let me write it in the blank space, greater than or equal to a negative number, then infinite solutions. So if your expression looks like this, where its expression absolute value of x is greater than a negative number, or the expression absolute value of x is greater than or equal to a negative number, you know that these two expressions right here are going to yield a all real number solution or an infinite solution. One more antidote before I leave you all towards this is that all the problems that we had to solve with two separate equations, when isolating the absolute value term, we end up on the other side with a positive number. So we have a positive 7 here, a positive 3, positive 11, and a positive 6. But when we're dealing with our special cases, we have negative numbers. We deal with these this -1 and this -3. So when you have a negative number on the other side, just like this equation, or just like this equation, you know that you're going to yield one of the two special cases, either the no solution or the infinite solution. So remember, if it's a positive on the other side, keep going. Make those two equations. If it's a negative number on either side, check what the inequality is and determine whether or not it's no solution or all real numbers. If you end up solving these two equations with the negative number, it will show that you don't know that this is already no solution or infinite solutions, and we will take points off. All right, that's it for me. Have a good one and study hard.